Okay. Thank you very much for the introduction and the invitation. I certainly enjoyed yesterday, especially the first session, getting to know all the work that's been done in this as part of this chair. And I hope my talk is going to live up to the high quality that has been shown so far. So this is a series of works that I've been working on for the past 5 years, maybe. In collaboration with Marie-Charles from Oxford, Eric Beckenschul, and my ex-PhD student, Jonathan Spence, and current one, Ian Powell. These are the references, but it's surprisingly a simple ideas here that I hope I'll be able to explain. The quantity of interest that we want to compute is some expectation of some function depending on a random variable x, with an indicator x being in some domain omega. So this quantity appears frequently in risk assessment when you are wanting to compute the probability of some catastrophic event or some quantity of interest on that event when that catastrophic event happens. So x will be a d-dimensional random variable, and omega will be, of course, in RD. So there are many reasons why this problem can be challenging. First of all, the dimensionality of x and omega can be relatively high, or at least high enough that it precludes the use of high-order techniques. The complexity of x and f, computing sampling x or computing f can be, those computations can be complex or require some approximations, some biased approximations, which you will see that we will use MLNC for that. And the rarity of the event, which is I'm not going to address here, but if you have any questions, I think you're in the right place. I know that the Al group here has a lot of work on this, using importance sampling or sequential importance sampling synthesis. But there are also reasons why this problem is easy in some sense. The structure of x and f allows us to use these techniques, hierarchical techniques like MLNC. And the regularity of omega and the density of x allow us to smoothen out this discontinuity, which will be the main problem, as we talk about in this background. And just for ease of presentation, I'll focus on the case when f of x is just a constant. This way, I'm only focusing on computing the probability of x being in some domain. But all the techniques that I described here are applicable to cases when f of x itself needs an approximation or is indeed not constant. So let me give you some examples. So the original motivation for this for me was from financial risk assessment, when one is interested in computing the probability of some expected loss of some portfolio Y given some risk factor R being larger than a max loss, so a maximum loss that we are interested in. It also appears in computing digital options or value options or other options that have a discontinuity, like when x, in this case, depends on a solution of underlying SDE. And another application, fancier application, if you will, is when one is interested in the probability of nucleodes from a nuclear repository leaking into some sensitive area. And so then the random variable x will be a PDE solution of some underlying randomness y. So the PDE will be some advection dispersion decay, and y will be the random porosity, for example, in the ground where the seepage is happening. And again, the interest in here, the interest is in computing probability of this solution being in some interesting domain. So in each one of these cases, we have an approximation where the probability is, where this expectation here is approximated by Monte Carlo. The SDE solution is approximated with the finite stepping scheme, or the Marema or Milstein, or the PDE is approximated with some finite element discretization, or finite volume discretization with a grid size and time step. So I don't need probably to spend too much time on multi-level Monte Carlo. And many people here will be familiar with this, but this will be our main workhorse. And we have the usual assumptions. I just want to emphasize one difference in the way I'm presenting those assumptions. So we have the work being to the power gamma L for an XL approximation of the random variable X. The usual bias computing when we compute any function G being of order or converging with rate alpha, as well as the variance. But here, the main difference of the previous presentation that I've seen is that I'm assuming the variance of the approximation on XL is converging with rate beta. Typically, you would have this assumption or this beta rate associated with G of XL. Okay, and of course, if G is Lipschitz, then that is the same rate, and that's precisely what I write here. So the usual multi-level Monte Carlo estimator. If G is Lipschitz, then G inherits the convergence rate of XL, of the approximate samples. And then you get the usual complexity of multi-level Monte Carlo, where if beta is greater than gamma, so the variance is converging at faster rate than the work is increasing, then you get near optimal complexity, okay? At least up to logarithmic terms if beta is equal to gamma. So that's the usual complexity that we have here. And the classical example is when G of X is just a Lipschitz function like a max, and we have an Euler-Marema approximation, then we get exactly this complexity of some power minus 2 log f some squared. Right. But as we said, our problem is G of X is a discontinuous function. So it's an indicator of X being in some omega. And to analyze this or to understand how the variance is converging for this particular G, we need two extra assumptions. And so the first one is the same as the variance assumption, but in for higher moments. So we assume not only that the second moment converges at rate beta, but all other, some higher moment than 2 is also converging at the same rate beta. So we're assuming slightly more regularity than would be required for just simple Monte Carlo or multi-level Monte Carlo. And we also have another assumption here, and this one is saying just we are bounding the probability of this approximations being within a neighborhood of the boundary of the set of interests, omega. So we're saying that the probability that this distance is less than delta is delta. So the density is bounded. It just means that not all my samples are concentrated at this boundary. So there's a significant number of samples that would be away from the boundary that I can use, where this functional is either 1 or 0. So with these two assumptions, then one can show that the variance of G now, G of XL minus G of XL minus 1. Recall, if G was Lipschitz, I could use the fact that G is Lipschitz to say that this is the same as the variance of XL minus 1, so converging at rate beta. But because of the discontinuity, I have to use these previous two assumptions to show that it's this order. So it's up to a constant that goes to 1 as the number of higher moments goes to infinity. So I'll refer to this constant frequently throughout my talk, but I wish to ignore it for the most part. But up to that constant, the rate is beta over 2. So I get half the rate as I would get for a Lipschitz function. And this can be seen because for this G, the discontinuous G that is, most of the time that this difference is going to be 0, right? Because we have a discontinuity, so it's either the function is either for the indicator is either 1 or 0, and the difference is going to be mostly 0. It's only when these two approximations are straddling the discontinuity, in which case we have a difference of 1, and so that should be multiplying the probability of being within that, being that close to the discontinuity, such that the two approximations are straddling the discontinuity. And it turns out that's exactly the essentially the difference between XL and X. Because we can relate the approximations to the exact sample. Okay, so then for discontinuous G, this is the complexity of the logarithmic terms again. So now we have beta over 2 rather than beta. And so with this introduction now, I still haven't got to the main methods here, but the mission is to find better estimators that recover the rate of approximation of X, beta, such that I don't see this continuity. So I get something that is as if I have a Lipschitz G. That's the goal of this talk. And that's the goal actually of many groups. And there's a lot of previous research on this. I'll try to give you a quick summary of it. And I say here non-exhaustive, not because well, I am lazy, but not because I'm lazy here in putting in, just because I might be forgetting something. And if I am, please let me know. But these are the methods that I've encountered. So there's path splitting, and this only works for SDEs. Oh, I should say the method that I would like should be easy to apply and applies to a large class of problems and for any dimension and hopefully for any approximation. That's the ideal method. So that with this kind of method, I can just apply it as easily as I can apply Monte Carlo and get the same and get the better improvement. So many of these methods will be applicable in particular cases or will require some more work than a simple Monte Carlo approximation. So path splitting is in particular only works for SDEs and only for Milstein approximations. I'll talk about this one later in the talk. Another method is to have an importance sampling exactly for the difference so that I concentrate most of my samples around the boundary. So that actually also improves the convergence rate. And this actually has been done by Mike and Shia. For these, it requires a little bit of designing of the importance sampling measure and the importance and figuring out what the importance sampling factor is. But it certainly works. Explicit smoothing is a different way where instead of looking at the indicator, one looks at some approximations that smoothes out the indicator. And this was studied in many different ways, but I think the most comprehensive one was in 2015 by Mike and Agapatian and Klaus Ritter. And one issue for this one is that one requires a lot of smoothness from the underlying density to get the, in particular, one requires infinite differentiability of the underlying density of X to get the optimal complexity. So the more smoothness one has, the more the less the complexity is. In particular, you require infinite complexity for optimal complexity, infinite differentiability for optimal complexity. Another one is so this one is smoothing out this continuity the same across the levels of multi-level Monte Carlo. You could also think like, oh, okay, why can't we just do it per level so that different levels have different smoothing? This was done in 2024 most recently. I'm sure done before as well. But this one doesn't actually improve the covariance, the variance convergence, because you still have to worry about the fact that you have now not only the approximation coming from the sampling, but also the approximation coming from this functional, and it turns out that those just add up essentially. You don't get improved variance convergence. Numerical smoothing is something that is also done not only in this context, but also in the context of QMC. There are many papers here. The most familiar, I am mostly familiar with the one by Raoul, Christian, and Simon Morgan and Shihab. And those, the basic idea there is that you take some random variables that are good enough, and you sample those random variables, or you approximate the integral of those random variables using a higher order method. And then once you do that, that smoothes out this continuity. And then for the remaining random variables, you do the just usual multi-level Monte Carlo. So this works. It requires a bit of finessing to understand what is the important random variable in this case, and also some root finding algorithm for every sample, so that the higher order method that you're using is still high order when you have this continuity. Another method is using integration by parts. So this now is relying on the smoothing effect of the density. If the density is smooth enough, you can use integration by parts by Millenian calculus. So you get rid of this continuity you integrate this continuity completely, but then you introduce the derivative of the density of X. And for SDEs, this works using Millenian calculus. It requires evaluation of the derivative, so it requires either numerical approximation of derivative or in this, for example, 2015 paper by Altmaier and Neumann-Kerr, what they do is they apply it directly to a Hester model and they evaluate the derivative exactly. So again, problems of applicability. Sebastian and Fabio have an interesting method where rather than looking at the indicator function, they look at the integral of that function. and they apply multi-level Monte Carlo in there. And then once they are done, they apply multi-level Monte Carlo there to get a functional approximation. And then they do a differentiation step at the end to get back into the indicator function, or the probability, that is. And this works, is just, it's requires a bit of care about the analysis there, because the problem there is that differentiation will make the noise will amplify the noise that is coming in the approximations. So if you have the approximations with any errors, differentiation will have even more errors. Another approach that just gets around the problem completely is to use some higher order approximation. And if this is available, this probably is a good option. So for example, for nested expectation, you can use quasi-Monte Carlo. For SDEs, you can use Millerstein. And what this essentially says that beta over 2 becomes good enough. So that you don't require you don't try to recover the higher order conversions, but because of the higher order method, you get something which has optimal complexity. And finally, adaptivity in Monte Carlo has been used to get around the problem with of the indicator function. So for level set estimation as far back as 2007, which I'll talk about a bit later, for nested expectation was done in Monte Carlo setting in 2011 by Brody et al. And for PDEs, assuming almost sure bounds rather than moment bounds that we had before, by Alberson and et al. In 2016. So this is even applying multi-level Monte Carlo, but again, assuming almost sure bounds on the difference. So that's just to say that this is a problem of interest that's been attacked multiple times in multiple contexts. And here I'm presenting two more methods to the arsenal of this research. Okay, so the adaptivity is where we'll begin, and that's within the multi-level Monte Carlo context. And the idea is very simple. For samples that are far away from the discontinuity, you can get away with a rough approximation. For samples which are close to discontinuity, you want to be a little bit more sure by refining the approximation so that you know which side of discontinuity the sample falls on. And the way to decide is by looking at this the distance to the discontinuity divided by some random variable which is arbitrary. Or you can choose it to improve the algorithm. But if this distance is large enough, then you decide, okay, I'm confident now that I'm far away from discontinuity. If it's small, then you refine further until this one is satisfied, until this condition is satisfied. And the refining is happening from 0, so at just level L, all the way to some multiple of the current level of approximation, so theta times L, for some theta between 0 and 1. Actually, it can be also greater than 1, I should say. It's just theta greater than 0, I should say. Right. Sorry, theta is between 0 and 1, yeah. Another example is for larger theta, but let's just focus on theta between 0 and 1. So now the question becomes, what is this theta and what is this sequence? And this we've discussed in series 2 works. So rather than specify what the sequence is, I'm just going to say there is a sequence such that the expected work of this adaptive samples on in expectation, it's still of the same order as just sampling XL. So we don't add significantly more work, which is crucial because now the variance has this expression. So it's 1 plus theta divided by 2. So if theta is 0, it means I'm not doing any refinement. This is just beta over 2 as before. But if theta is positive, which means I am doing some refinement, then I'm getting improved variance convergence. In particular, if beta is greater than gamma, slightly bigger than gamma, then you can get theta to be 1, and you get this is 2 to the power minus beta L. So you recover the variance convergence rate of a Lipschitz function. So this, for example, for Euler Mariama, the example we had before with an indicator function, adaptive unknown C will have this complexity here. So epsilon to the power minus 2 log epsilon squared. The same if G was Lipschitz. Classical multi-level Monte Carlo will have a reduced or increased complexity. Okay, and this actually does work in practice as well. You can see This is Monte Carlo. These two are multi-level Monte Carlo, two versions of multi-level Monte Carlo, which are classical in the sense of using either too much refinement per sample, or too little refinement for every sample. And the adaptive one achieves the better complexity. Now, with that being said, there's a good and there's a bad of sample adaptivity, and I do like to emphasize where my methods don't work. So the good is that it does achieve MLNC complexity, which is similar to one that MLNC would achieve for a Lipschitz function. So that's good. It's also, as you can see, I didn't assume any other things besides the initial assumption that I had on the higher moments and the boundedness of the density around the boundary. So it's applicable to almost any model and approximation. So it works for Euler-Mariema, for Milstein, it works for nested expectation, for SD approximation. It's a simple to apply method. However, the problem is that adaptivity mitigates this continuity. We achieve the higher convergence rate, but it does not remove it. And the main problem there is that XL, we saw that we assume that higher moments converge at the same rate as this variance. So it's always rate beta. But for the indicator function, higher moments converge at relatively worse rates, because taking the power here to Q for this higher Qth moment is the same as taking it to square, because this is just 0 or 1. So it's always the same convergence rate. And so since you're taking 1 over Q, you have worse convergence for higher moments. What this means is that if you look at, for example, the kurtosis of the defined as the fourth moment divided by second moment squared, this becomes the second moment to the power minus 1, because this one is just the second moment. It's the same as the second moment. So this is just the second moment, 1 over the second moment. And we just said that we did improve this convergence rate. So the variance of the difference is for the indicator function with adaptivity is improved, but it means that the kurtosis is worse. So while we achieved our goal in improving the variance convergence, we also made the kurtosis worse. So this means that for multi-level Monte Carlo, where variance estimates are required, for error estimates, for sample optimizing of number of samples, this is problematic. It means that those estimates would require increasingly more samples at deeper levels, which is not what you want in a multi-level Monte Carlo setting. So the kurtosis issue has to be solved with algorithmic means, using continuation multi-level Monte Carlo, using some Bayesian updates of the sample of the variance estimates, so that earlier levels can be used to stabilize the estimates level. But also it means that nesting estimators of this kind is limited, because those estimators, as we saw, require higher moments. And if you are nesting it once, your higher moments are also then worse, converge worse than before. And then if you nest it again, it converges even worse. So you're always getting worse and worse convergence as you nest them. Compare this, for example, to nesting Lipschitz, MLC estimators of Lipschitz function. That's actually very possible, assuming that you can control the higher moments or use methods that don't require such higher moments. So, for example, we argue in our publication on credit value adjustment, where we have triply nested expectation, is that biased MLNC is a better alternative than unbiased MLNC. So because nesting it does not require these higher moments. Also, antithetic estimators, which are those that assume smoothness of the underlying quantity of interest, those are not going to be applicable, because we still have the discontinuity. Even though, again, we have the improved variance convergence, it's still a discontinuous function. Before I discuss the second method, I just want to make a quick mention of the other risk measures. We talked about the probability, but we can also talk about VARD. So this is the value at risk, which is used traditionally in finance, but it's increasingly used also in industrial applications to assess the levels at which a certain risk is happening. So it's defined this way. It's just saying essentially what is the minimum loss for which the we are confident that or what's the minimum loss for which the probability is above a certain confidence interval of achieving that loss less than that. But this one requires essentially a root finding algorithm where at every step we have to compute this probability. And this probability we just saw that we can compute using MLMC. So by having a root finding algorithm that changes the accuracy of computing this probability as the iterative algorithm progresses, one can achieve the same complexity at just estimating one of those probabilities exactly, accurately, I should say. So it means that I can still estimate this var at order epsilon power minus 2 times log epsilon squared, for example. Even though I have to estimate these probabilities multiple times, but just again refining that estimate in the root finding algorithm as I go through it. If you prefer a better method or a more disciplined method, you can have an MMC version of the stochastic approximation algorithm. So this one is just for root finding algorithm that where an expectation is involved. And it has the same structure as a multi-level Monte Carlo, traditional multi-level Monte Carlo, but now instead of having Monte Carlo averages here, you have the stochastic approximation algorithm, which depends on the learning rate, quote unquote learning rate. But it's the same kind of like multi-level stochastic gradient descent, or the same ideas as multi-level stochastic gradient descent, but in the context of root finding. But since you have this now as a multi-level Monte Carlo approximation involving an indicator function, then you can use the same kind of adaptivity ideas here in this context. And this actually Johnny did with other collaborators more recently to improve the complexity of finding those roots back to epsilon power minus 2. I will skip C var. So conditional var is essentially it's called the expected shortfall. It's the expected value of the loss given that the loss is greater than the var estimate that we just had. I'll skip it by just saying that it's not a problem, even though it has an indicator in some sense, because of the way, because it can be written as a minimization problem involving a Lipschitz function. It actually can be solved very efficient, or can be approximated very efficiently without any problems using traditional multi-level multiplier. Another risk measure is to find a level set of a function. So, for example, if you are interested in the expected value of some random function now, depending on some special variable y, and you're interested in all the values of y for which this expectation is 0, then you might want to approximate that expectation with a Monte Carlo sampler, and then get a corresponding approximation of the level set. And then you can have the same kind of adaptivity in the setting, which is similar to Melin-Guibou. So where you have a discretization of the space of y, for example, using uniform discretizations with 2 to the power d L0 for some level L0 cells. And then for each one of those cells, you have some random, or some, I shouldn't say random, some number of points that you use to approximate the expectation at those points, and then use those approximations to get an approximate functional using some interpolation method, for example. So within each cell, we can have an approximation of the expectation, and then we can get the level sets as just a union of all the cells, of the level sets of all the cells. And then using a similar idea to, or using a similar refinement criteria, depending on the distance to the discontinuity, in this case 0, divided by the error, again, the same as before. We can also decide if we want to refine based on a sequence. And it turns out that under a similar assumption to before, of essentially bounding rather than the probability of being on the boundary, bounding the Lipschitz measure of being on the boundary or close to the boundary, then you can get an improvement in the complexity of. So this is the complexity when you don't do adaptivity that depends on the dimensionality of the ambient space, and this is the complexity when you do adaptivity, which depends on the dimensionality of the level set itself. I realize that this is a bit too fast. It's just to say that by doing adaptivity, one can focus their effort or focus the work exactly on the level set that's which has a lower dimensionality. It remains to be seen if this can actually be amenable to multi-level Monte Carlo approximations. Okay, so far we've discussed adaptivity, but adaptivity does not actually utilize the smoothness of the underlying density. And as we said, we have these smoothing techniques like Malevin calculus, which do, as well as the numerical smoothing. So what we wanted to have is a method that is applicable to SDEs, because we have to focus on a certain model that exploits the underlying smoothness, and also that sort of exploits this kind of smoothness. So let's focus on SDEs then. Let X be the solution to that SDE at some final time. Let's call it 1. And we have the same approximation XL, and we'll look at the filtration FT. So we are now focusing on the difference of indicators, but now the XLs are some discretizations of the underlying SDE. And the key point here is conditional expectation, in the sense that if I condition this difference on some underlying, on some filtration at some 1 minus tau, so before reaching the final time, then this quantity of interest, delta QL, has the same expectation as delta PL, so it's unbiased. However, hopefully it will have the same kind of work as delta PL and improved variance convergence, because this one is integrating the discontinuity. So that's the key point. And in fact, if I take tau to be HL, where HL is the time stepping in the my underlying numerical scheme, so I go all the way up to 1, or HL before at the end. So I take the path all the way to the end until HL, and then I do something. So if I use Euler-Mariano for that last step of the numerical discretization or the time stepping scheme, then the conditional distribution, I know exactly what it is. It's a Gaussian, right? Because I'm adding an Euler-Mariano, I'm adding just the Gaussian there. And if I condition on the previous step, I have a Gaussian invariant. So we can compute this conditional expectation here exactly, because I can involve the Gaussian CDF. And so the point is that then we can have this expectation here, I'm making time dependence explicit, of the XL at time 1 being in storage. This should be omega, given that the previous time step is x, so that call that function g of x. And then if I look at the second moment of this difference, that's just the expectation of the difference of g's, this g in particular, square. And now this g is differentiable, so I can take the derivative and then take this difference here squared. This difference squared is converging at rate beta. This derivative now is mostly 0 for most of the time, except for the paths that are close to this continuity. And those are, because of the size of the Gaussian, are exactly order square root of HL. But then the size of the derivative is 1 over square root of HL because of the Gaussian. So I get the square of the this times HL. So the end result is that this expected value of delta QL squared is HL beta, which is what I want, but minus half, which is the price I have to pay. But the cost is the same. There's no additional cost to this estimate. So what this means is that this now, if Milstein, where beta is equal to 2, I have the variances improved as before it was for delta PL, it was HL, now it's HL 3 over 2. So great, that analysis complexity is improved, and it's as if I have a Lipschitz function. For Euler-Mariano, however, because beta is equal to 1, I don't see any improvements. So this, again, I don't have a method that works for all approximation methods. For the antithetic estimator as well, if I have an antithetic estimator on the SDE paths, this also doesn't work, because even though I have improved variance convergence there, actually it will involve the second derivative of G, which this one blows up even faster. So this actually is leads me to path splitting, where that's done by Glasserman and Mike and Borges, where rather than just splitting at the end point, you can split at any point between 0 and 1 and use Monte Carlo approximation to approximate the conditional expectation. So we have two extremes. When tau goes to 0, it means I'm splitting at the very end. It means that so this now tau is 0, so it's F1. So that's measurable. So I get the expected value of delta PL squared. So that's order HL beta over 2 approximately. So the variance is worse, but the work is free. When tau is equal to 1, it means I'm splitting at the very beginning, but then I have a Monte Carlo estimate for every one of them. It means that I have a lot of work, but if I look here, because I have here I'm conditioning on F0, and this becomes then just the expectation of delta PL squared. So I get the weak rate or twice the strong rate. So I get the better variance. And taking this to the extreme, I can have this branching estimator where at the halfway point, I branch twice. So I compute, I have the underlying, for example, Brownian motion here. At the halfway point, I branch twice. And then at the halfway point between, in the remaining time, I branch twice again. And at the halfway point, I branch twice again. And in the end, I have a number of samples at the, which are identically distributed because each one of them is just depends on underlying Brownian motion. But for each Brownian motion, I can compute the difference, delta PL, of this difference of indicators. And for all of them, then, since they are all identically distributed, I can take the average. And I get my new estimator, delta PL, paragraphic PL. So now this estimator is approximating something, but it's unbiased. And now I just need to worry about what is the variance and the work that is this method, this estimator have. So under similar assumptions to before, namely that the density is not unbounded around the boundary, but here not just the density, but the conditional density is not unbounded, and the blowup is controlled. So under this condition, which we can show for certain SDEs, we have that this new estimator is unbiased. The work is not much more than the work of just a single sample, FL, this in here. And the variance is HL for beta, so the nice variance, plus beta over 2 plus 1. So I get an additional factor here relative to just a simple estimator of depth. And actually, this works not only for these simple estimators like Euler, Mariam, and Milstein, but also for the antithetic, where I have similar improvements. So let's just work out some examples. Euler, Mariam has beta equal 1, so it means that here I have 1.5, HL is 1.5, and beta is equal to 1. So this one dominates, and I get that the variance of this new estimator is as good as if I had the Lipschitz function, which is what I wanted. For Milstein, beta is equal to 2, so this one dominates. No, actually, they will be the same order. So I get, again, the same as a Lipschitz function. For the antithetic, this one will dominate because it's 1 plus half, essentially, again, ignoring these constants. And I get almost the same as a good variance for a Lipschitz function. But in all cases, I get the optimal complexity of multi-level parallel. Not only that, we also prove bounds on the kurtosis. Essentially, if I look at the this new estimator, so these are in squares for both Euler, Mariam, and Milstein, and as well the antithetic, all of them have bounded kurtosis. While if I look at the just the original one, as we saw, the kurtosis blows up. Okay, so I have 1 minute to conclude. So we saw adaptive methods which deal about with the problem of discontinuity. They are versatile, they're easy to use, very simple, but they suffer when the higher moments are needed. Branching is applicable to a wide range of SDEs and estimators. It's fairly easy to implement as well, although it does require a bit more work in sense of coordinating the paths. But it doesn't need. It's similar actually to normal plus smoothing because we are using Monte Carlo to smooth out the Monte Carlo or some averaging of the paths to smooth out discontinuity. But it's not. It's more natural in the sense that it doesn't need root finding or anything because it uses underlying Monte Carlo method. So these assumptions of this form that I showed you, where we have either conditional or non-conditional bound on the density close to the boundary, those can be proved for a large class of problems by assuming smoothness of the underlying density of X, which we can prove for elliptic SDEs with Brownian coefficients, as well as assuming that the domain or the set omega is a Lipschitz graph. So where to go from here? Well, we can, rather than just look at the risk assessment in the sense of computing probabilities, we can think about computing sensitivities. using bumping, for example. Branching, I suspect, will be very helpful there. And actually, I have a PhD student working on this now. We can look at pricing other options like a barrier, where not only we have a discontinuity at the final time, but we also have discontinuity throughout the path. We can apply other methods, for example, particle systems, which would require proving these kind of conditions on for particle approximations. This is something that I also think that will be very natural, which is not just approximating one discontinuity, but approximating a series of discontinuities to approximate a CDF, where adaptivity, I think, will not be as good as branching, but one will need more analysis to see how much the conditions will, well, taking the limit as the number of points of discontinuity go to infinity, how does the variance in the functional approximation decay? And the extension to SVDs is quite natural as well, but then analysis probably is a challenge. Okay, so I have many references there, which I realize are too difficult to capture, but the slides will be, once I correct the typos, will be online. Thank you.